This video is going to go through the easy questions on Newton's laws of motion. Question 1a asks you to state Newton's second law. So the definition for Newton's second law here I got from the definition sheet provided by the WJEC. Sometimes when you're asked to apply Newton's second law, it wants F equals ma, but if you are asked to state it, it is after this definition. So the rate of change of momentum of an object is proportional to the resultant force that is acting upon it. And the second mark, you need to say that the change of momentum is in the same direction as the force that has been applied. For question 1b, at its launch, a rocket and its contents have a total mass of 150,000 kilograms. The engine produces a thrust of 3,500,000 newtons. Figure 1 shows it, and calculate the weight. So we know how to calculate the weight of an object. Weight is equal to the mass of the object times the force of gravity, which is going to be 9.81. So you're going to take the mass from the question, times it by 9.81, which is on our information sheet if we've forgotten. And the answer that you're going to get is 1,471,500 newtons. So 1,471,500 newtons. One C is going to be to calculate the resultant force on the rocket during the launch. So we know, I'm going to annotate our drawing up here. We've got 3,500,000 going up, and we've just calculated the weight going down as this number here. So to work out our resultant force, that's our overall force, we're going to do the one that goes up, take away the one that goes down. So what you're going to type into your calculator is this. And the answer you're going to get is this number here. So 2,030,000 newtons. Question 1d, calculate the acceleration of the rocket at launch. So this is where we're going to use our force equals mass times acceleration. We just worked out the overall force. And that was this number here. So to work out our acceleration, we're going to do the force divided by the mass. So we're going to do that number that we just worked out, divided by the mass of our rocket, which was 150,000. It's 13.5 meters per second squared. Moving on to 2a, new question. We've got a figure that shows a skier being pulled forward by the rope at constant velocity along a horizontal section between two ski runs. It is in bold, but just realise there it does say constant velocity. That means zero acceleration. The tension in the rope is 50 newtons and the total mass of the skier is 85 kilograms. Name each of the forces to start with. So I'm going to give a couple of alternatives for some of these, but we'll start with A. So that's our force going backwards. So we can call that the drag, the air resistance, or it could be the friction. Any of those are acceptable. B, that's going forward. That's the tension in the rope. It does say in the question, it calls it the tension. C, so that's our force going down. That's going to be his weight due to gravity. And then D, that's the force going back up again. That's our normal reaction force or our normal contact force. It is important when labelling these to use the word normal because that shows it's at 90 degrees to the ground. Question 2b, determine the magnitude of force A and explain your answer. So we know that it's going at a constant velocity. So if we use our F equals ma, acceleration is equal to 0. That means our overall force must equal 0. So if we look at this person as a whole, his forces, if we look at them horizontally and vertically, overall it's going to equal 0. So we've been told the tension, which is force B, is equal to 50 newtons, what must force A be? So because there's no horizontal force, force A must equal the same as force B, so it must equal 50 newtons. It does say to write our explanation as well, explain your answer, and that's what I just said. So there's no resultant force horizontally because there is no acceleration. Therefore, our forces have got to be equal. Moving on to 2C. The rope towing our skier suddenly breaks, so there is no longer a force B. However, the skier continues to move forwards. Force A remains constant. So force A, if you remember, is the drag on him, what's going backwards. Considering the forces and explain whether he accelerates or decelerates. So you can probably already picture in your head, he's going at a constant speed, the force pulling him forward stops, therefore he is going to decelerate. We just need to explain why. So we need to say, first of all, there is now a resultant force which is acting on the skier. So before, even though there were forces, there wasn't a resultant force, there wasn't an overall force because they were balanced, but because force B is gone, now there is a resultant force. It's going backwards, it's in the opposite direction to the way he was travelling. So he was travelling forwards, but this force is going backwards. So there's our first 2 marks, and the final one is just to state what we already know. So that means our skier is going to decelerate. So our skier decelerates. Assuming the magnitude of force A remains constant as determined in part B, calculate the deceleration of the skier. So force A, we worked out earlier, was 50 newtons. We know his mass from earlier was 85 kilograms, so we're just going to use F equals ma, rearrange it, acceleration is force divided by mass, to work out his acceleration. Obviously this is going to be a deceleration because he's slowing down, but it's still the exact same sum. So his deceleration is going to be 0.59 meters per second squared. Question 3a. A remote control racing car has a mass of 0.6 kilograms. It can accelerate uniformly from rest to 5.2 meters per second in 1.6 seconds. Calculate the acceleration. So the equation for acceleration is the change in velocity divided by time. There are other ways of writing this that are on your equation sheet if you don't recognise this one, but it's our final velocity take away our initial velocity divided by time. Because it starts at rest, its change in velocity is just the final velocity divided by our time. So you're going to get 3.25 meters per second squared. And then we've got to calculate the resultant force, so we're going to use the mass there. F equals ma. So we're going to take his mass of 0.6, it's in kilograms, so we don't need to do anything to our mass, times it by what we've just worked out, and you're going to get 1.95 newtons. Don't forget to add your units. This is in force, this is a force, so it's going to be in newtons. After 1.8 seconds, the motor is switched off and the car decelerates uniformly until it stops, and there's our deceleration, 0.8. Given the force is the only force acting on the car, calculate the magnitude of this force. So there's a lot of words there. We are just working out what force has caused this deceleration. So we're going to use the same equation as before, but with the different numbers that we've just been given. So we're going to take the mass of our car, which is 0.6 kilograms, times it by our deceleration, 0.8. So it's going to be 0.48 newtons. I'll work in as its resistive force. So it's drag, it's friction. That's what's pulling it back and stopping it from acceleration or remaining at a constant velocity. 3D, assume the resistant force was constant throughout the motion. Use your answer from part B to calculate the thrust when the racing car was accelerating. So we worked out earlier we had a resultant force when it was accelerating, which was 1.95 newtons. That's from part B, that's what it says to use. We know the friction, which we've just worked out, We know what's stopping it from going forward, and that's the 0.48 newtons. That's from part C. So its overall force, its resultant force, just to remind you of how we'd work that out. So if I was to draw our car, for example, here, we've got our forwards force. Let's call it our thrust, because it does say to calculate the thrust. We've got our backwards force, which I've called our friction here. We could call the drag. And then we've got our resultant force, which is our overall force. So it's the one forward, take away the one backwards. So our overall is thrust, take away our friction. So let's pop our numbers in there. We've got the overall force, 1.95. We don't have our thrust, and we do have our friction. So that means to work out our thrust, we've just got to add these together. 2.43 newtons. Question 4a. A brick of mass is resting on the floor as shown in figure 1. Name the forces. So going up, our force A is going to be our normal reaction force, or our normal contact force. There are other ones you can call it. However, I'd stick to one of these two and always use the word normal just to ensure that you get the mark as well. And B is our weight, or we could call it our force of gravity. So it's the weight of our block pushing down on the earth. Question 4b, state Newton's first law. Again, I've copied this from the definition sheet. A body will remain at rest or move with a constant velocity unless it's acted upon by a resultant force. That's an important word there, a resultant force, an overall force. Lots of objects have forces acting on them, but if they balance out, it will still remain stationary or at a constant velocity. Part II, explain how it can be applied to the forces acting on our brick up there. So we're going to say, first of all, kind of like what I just explained, the brick here is stationary. That must mean it has no overall resultant force acting on it, okay? So it must have no resultant force acting on it. And in this one, there's 3 marks, so we've just got to make sure we state everything that we can. That must mean here that our force A, our contact force, must be equal to force B. That's the only way, given those forces, that this block is stationary. Question 4c is to state Newton's third law and explain how it applies to the brick. So Newton's third law, I would say, is the most complicated to get your head around. So if you listen to my explanation here and don't understand it, I would spend 5 to 10 minutes looking up some other YouTube videos on how to explain Newton's third law. So part I is just to state it. If body A exerts a force on body B, then body B will exert an equal force in the opposite direction. So the forces are equal and opposite, but what's important to note about this is we're talking about body A exerting a force on body B, and then body B exerting a force on body A. So we are talking about different items. So to apply it to this brick, there are 2 different Newton's third law pairs that we can talk about. So one is the downwards force of gravity, which is caused by the earth on the brick. It's going to be equal and opposite to the upwards force of gravity caused by the brick on the earth. Or alternatively, you could talk about the contact forces. So we're not talking about the fact that the contact force is equal and opposite to the gravitational force. That's just because the brick is stationary. Newton's third law always applies. So if we talk about the contact forces instead, we're saying the upwards contact force caused by the table on the brick is equal and opposite to the downwards force caused by the brick on the table. Question 4d, a horizontal force is applied to the brick which causes it to accelerate at 0.2 meters per second squared. Use Newton's third law to calculate the size of this force. So we're going to use F equals ma. We're working out the force, so we're going to take the mass that we had earlier, 1.5 kilograms, times it by our acceleration, so we're going to get 0.3 newtons. That is our horizontal force. Question 5a, a block of wood of mass 5.2 kilograms is sitting on a smooth table and it's acted upon by a force of 5.8 newtons. Calculate the expected acceleration. So at the moment we're presuming there's no friction, so that's our only force. So we're going to do F equals ma. So we've got our force this time, we've got our 5.8 newtons, our mass, and we're working out the acceleration. So we're going to do our force divided by mass, which is 5.8 divided by 5.2. So you're going to get 1.1 meters per second squared. Question 5b, the movement of the wooden block is investigated using a data logger, and here is the graph that shows its velocity divided by time. Calculate the actual acceleration. So that's going to be our gradient. So we're going to use a gradient triangle. Spelled gradient wrong. That's going to be our gradient. So it does say in the mark scheme here, show that you've used a triangle to work out your gradient. So what I always do is look for a nice point where I can draw my gradient triangle from, a place where it's really easy to read. And the gradient is going to be the change in y divided by the change in x. So I'm just going to draw my gradient triangle. Hopefully yours is going to be a little bit neater than mine. I'm going to draw it on there so I've made clear to the examiner what I have done. So gradient is change in y divided by change in x. So our change in y here, 0.25, take away 0, which is just going to be 0.25 over 0.8, take away 0. And if you work that out, your acceleration should give you 0.31 meters per second. Question 5c, use the actual acceleration calculated in part B. So we just worked that out, I'll copy that over, 0.31 meters per second squared, to calculate the resultant force. So again, we're going to use our F equals ma. This time we're working out our resultant force. So we'll pop in our acceleration and our mass. So our mass was, that first 5.2 times our acceleration. We're going to get 1.612 newtons for the first part. Then as we move on to question 5d, it says the acceleration is different. That's because there is a resistive force, a friction, a drag, air resistance, something like that acting between the block and the table. Work out the resistive force. Remember that the block is being pulled by a force of 5.8 newtons. So if we draw our block, we know that there is 5.8 newtons going this way, presuming that's the way it's moving. We know that backwards, we've worked out, actually we don't know our backwards force, that's our resistant force, I'll label that R because it's our resistance force. And we know that our overall force, we worked out last time, is 1.62 newtons. So our overall force is equal to our forward force, take away our resistant force. So that means our overall force, which is 1.612, is equal to 5.8, take away R. We want to work out R, so we put R on this side, 5.8 take away 1.612, and that gives R at around 4.2 newtons. That's our resistance force.